Yes. Jessica, right? We said I did just to help me. I realized I just knew it, but it's very helpful to have it. You're okay.
There's instructions on
Oh, yeah.
Oh, because it's just showing like one number.
Yeah, wait, the second one is selling. Okay, great. And Cyber. Okay, great. Did I email you that? Did I answer your question? Yeah. Okay, and wait, say it again? Purus. Oh, I'll give her an X, Purus. All right, I knew it Purus, but it wasn't spelled that. Okay, yeah, Purus. What's the one here? Francisco. Oh, just help me jog my memory. Celine, right?
Yeah,
Celine. Yeah. All right, folks. I noticed that the volume it kind of trailed off there, so I'm thinking that most of you are done chatting about this. So let's review. Now, first of all, I know that a couple of you were not here on Monday, so you might not know these things, and they might not be in your notes. But let's just keep in mind, anytime you're absent for the rest of the semester, you can watch the video again online, because I've got my laptop right there. I'm recording class, so if you miss a class, I strongly encourage that you go back and watch the class so that you can fill yourself in on all those gaps. And that's it. So here we go. What are the definitions of rational and irrational numbers? So just what's that definition? Chelsea, get us started.
The rational numbers are written in the form of A and B, with A and B as integers. They terminate or repeat, whereas irrational numbers.
Wait, stop right there. Okay, so rational numbers are ratios or fractions. We have an integer over an integer, and they can be written as fractions, and you can recognize their decimal as something that stops or repeats. Okay, perfect. So that's rational. How about irrational? I'll go with volunteers first, but then I'll just call on you. Yes, go for it, Dave.
It doesn't terminate or repeat.
What doesn't?
The irrational number.
What of the number?
The decimal.
The decimal, very good. So the decimal representation does not stop or repeat. Keep in mind, an irrational number, you could write it down in a way that does stop and repeat, like the square root of 2. You know, that stops, it's just 2. But it's under a square root sign, and if you actually write that out as a decimal, then it's 1.141096, whatever it is. So yeah, the decimal representation doesn't stop or repeat. And you recognize an irrational number by the fact that it's either a square root or pi. Okay, so those are rational and irrational numbers. Very good. What is interval notation? What is it? We called it by a cute name the other day. Yeah, wait. So, did I say it again? Selenet. Yeah, selenet. So, it's a lazy person's number line. Exactly right. So if you wanted to represent a solution set of a problem, like I'm thinking of a number between 1 and 10. So this is how I write it as an inequality. I'm thinking of a number between 1 and 10. This is how I write it as a number line. I'm thinking of a number between 1 and 10. So I'd shade both circles because I'm including 1 and 10. I shade everything in between because those are the numbers I'm thinking about. This would be the inequality solution. This would be the number line solution. The interval notation is the lazy person's number line. So you just take the two numbers, 1 and 10, and then you use either a parenthesis or a bracket, depending on if it's a less than or equal to or just less than. In this case, what do I use, a bracket or a parenthesis? This is a bracket. So there we go. That's the lazy person's number line. It captures the exact same information that you had on the number line. It's just written much faster and easier. And you can type that on the keyboard, right? It'd be very easy to type to someone's bracket, 1, 10 bracket. You can type it to someone. This would be rather challenging to type to someone via email. Okay, wonderful. So when using interval notation, what symbols do you use to mean included and shaded? So which are all the symbols that go along with included / shaded? What are those symbols? Who would like to tell us? Yes, Joseph. Well, union is a particular symbol that allows you to talk about multiple intervals simultaneously. But, so no, that's not the answer to the question. Which symbols go along with included or shaded, Josh? Brackets go along with included and shaded. What other symbols go along with it? Yeah, so I don't know why I'm having such a hard time with this. Selene, no, it's not Selene, it's Selena. No, Selene. I'm having a really hard time. Say it one more time. Selene. Selene. There we go. Selene. What's another symbol?
Closed circle.
A closed circle. And then finally, somebody else? About Guadalupe? What other symbols go along with included and shaded? Yeah, less than or equal to and greater than or equal to. So all those symbols mean that you are including the number in your solution set. So what symbols go along with not included or not shaded? Who said that?
Parentheses.
Yeah, Jessica. Parentheses. And what's the other symbol? Irvin? What's that? Yeah, an open circle. And then Jackie? Yeah, strictly less than or strictly greater than. Okay, and where does infinity go? Yeah, infinity is treated as a not included because you can never get to infinity on a number line. It's just, that's the direction if you keep going. All right, well, wonderful. So these are some of the symbols that we talked about. Quite a few of you have already gotten onto the More website and sent me an email. You said hello. So how do you, if you've already been there, how do you type infinity into More? How do you type infinity on your keyboard? Yeah, Bryce. It's just 2 lowercase o's. That's right. Okay, well, folks, that's just a quick little review. That's it. We start the class by just reviewing concepts, the main concepts that we talked about in the previous class, and now we're ready to keep on going. So, today's excitement. We are, let's see, today's January 16th. We're going to proceed and move along through Chapter 1. We're going to finish 1.1 and then move into 1.2 and 1.3. I think that we can do all of that. We have 2 hours and 20 minutes. This should be possible. Notice that on Monday, we don't get to come to school together. We have to take the day off. Now, if you want to, I'm still going to be here. I'll just sit in the room with the lights off. So if you still want to come in, we can hold class. Anybody? Anybody? No, you're going to take the day off? All right, well, that's fine. I'll stay home too. So no school on Monday, but the fact that we don't have school on Monday does not change the fact that you still have homework due online. Now, you might say, oh, Mr. Sheet, I don't want to work on a day off. It's a holiday. Why should I work? Well, you don't have to. You can do it the weekend before Monday. Nobody's saying you have to do this stuff on Monday. It's just due by Monday. So probably my best recommendation for you would be that after today's class is over, we will have covered 1.1, 1.2, and 1.3. Right now, tonight would be the best time to go online and start doing those practice problems because it's fresh in your mind. And then, finish it, what's today? Wednesday? You have all day Thursday, all day Friday, all day Saturday, all day Sunday. You don't have to do any work at all on Monday. It's a holiday. You take the day off. All right. Before we get started, let's take a look at that syllabus quiz. Let's review it real quick, just so we're all on the same page with the policies. And then as during the break today, our 10-minute break, I'll take your syllabus quiz and your personal information sheet. So I'm going to practice your names going around the room. I need to bring a what to every class? Chantal? A graphing calculator. Bring that graphing calculator to every class. Really take it with you everywhere you go, right? Keep it in your pocket. If you go to a party, bring it. If you go to a restaurant, bring it. You never know when you're going to need your graphing calculator. Thank you, Chantal. By the first week of class, I need to log on to the website. Yes, sir. Thank you so much for coming. I was unable. Now watch. It's just going to play right now, I bet you. I was unable to get the volume to play. Oh, no, it didn't. No, yeah, it didn't do it. Thank you very much for coming over. Okay, I can't really see anymore, but what website do I need to go to, Joseph? Yeah, the More website. Can I borrow yours? Thanks. Okay, and next, the notes packet. The notes packet is worth 20 points, and I will lose what for every problem blank? Oh, let's go on over here to Syra. Yeah, exactly right. So when I collect that notes packet on the day of the test, every problem that you have blank or incompletely solved, I just take a point off. Of course, I want you to turn it in completely finished. Okay, practice test. The practice test is worth 20 points, and I'll lose what for every problem blank? Let's go to Isaac. Oh, 1 point as well. Okay, more videos assignments. I will watch the videos when? Selling it? Before class. Yeah, before you come to class. And the more online practice, always do when? Beth?
The more online practice is always due. I didn't put that in.
Well, that's okay. Anyone help her out? When does it due?
Paper test in the week.
It's always due on the Monday after the lesson was taught. Is that what you all have on your paper? It says always due on the Monday after the lesson was taught? Yeah, so always. So whatever we cover this week, all of that material is due the following Monday. Okay, tests. If I'm not in class on the day of the test, I will receive a what on the test? Let's see here, Francisco. Right, a 0. I mean, you weren't here, you didn't take the test, so that'd be a 0. However, if I'm going to be absent on the day of the test, I have what? Celine? Yeah.
Oh, one opportunity.
One opportunity to take the test at the testing center within 3 calendar days of the test date. So I expect everyone to be here on the day of the test and you take the test. But if you have some sort of emergency, your car breaks down, you have to go pick up your kids, who knows what, you have one opportunity to take your test in the testing center instead of in class, but only once. So if you're absent on 2 testing days, you can retake one of those tests, but the other test you're just going to get a 0. So obviously you need to be in class on the day of the test. Okay, final exam. I will keep all of my what? Abe?
Chapter tests and quizzes.
Yeah, absolutely. I don't think we have any quizzes, but yeah, you keep all of your chapter tests and review them before the final exam. Okay, I will be in my seat at the start of class time, which is when, Jessica? Yeah, by 8 a.m. Very good. I'm allowed 2 tardies for free. Starting with the 3rd tardy, I'll lose what? Jackie. Yeah, 5 points from the final exam. And then I'm allowed up to 2 absences for free. Starting on the 3rd absence, I'll lose what? Josh. Yeah, 5 points off the final exam. I can be absent a maximum of 5 times, excused or unexcused. On my 6th absence, I must meet with Mr. G during office hours to discuss my progress. Otherwise, I will be withdrawn. Yeah, or dropped. Yeah. Obviously, I don't want to drop any of you. But if you're absent a whole bunch of times, that's like a crisis. And like we need to meet and sit down and talk with each other because you can't just keep on being absent. None of you are going to have a lot of absences, right? I'm just saying theoretically, if someone were to have lots and lots of absences, you'd need to come in and sit down and chat about it. Okay, and I can earn extra credit for perfect attendance. If I have 0 tardies, I earn, hold on everybody. What will you earn, Victor, if you have 0 tardies? Yeah, 5 bonus points on the final. And if you have 0 absences, what will you earn, Erica? 5. Yeah, 5 more bonus points. Okay, before the day of what? I will come in for office hours. Syra. Yeah, by the day of the 1st exam. Come into my office. If not, you'll lose what from your test, Bryce? Oh. Yeah, 50%. Obviously, don't do that. Just come into my office. You can come. We have office hours right after this class. So today would be a great day for people to start coming up. Just a whole group of you can come on up to my office. I'll sit down and I'll just look at your notes real quickly, and then you can all leave. So it's a really fast process. Finally, if I earn less than what on a test? Gosh, I think I really have. Hold on, everybody. Chelsea? Yeah, less than 70, then Mr. G will record my grade as a what in the grade book, Beth?
0.
Yeah, 0. I know that sounds harsh, but I'll put the real grade in as soon as you come in and review your test with me. Okay, wonderful. Well, there we go. Those are all the key policies. Now we're all on the same page and we know what to expect. Oh, can I change the slide real quick? Yeah. Thank you, sir. Hey, thank you for your help. Okay, so yeah, turn those in during the 10-minute break, and here we are. Okay, go for it. So, did we finish looking at all of these essentially? Okay, I'm sorry, I'm going to use the mouse one more time. And did we finish doing all of these? We did? Okay. And oh, right, and then we got to here. Where did we leave off? Okay, great. So let's go ahead and look at number 7. I'm done with the mouse. Okay. Thank you very much, sir. I really appreciate you coming in. All right, so number 7, and this is a very fun problem, because at first glance, it seems kind of tricky. Like, what on earth? How do you do this? We want to show the interval notation for all the numbers in the universe such that x just isn't equal to -3 or 4. That's what that says. For number 7, we're saying, number 7, we're looking at the set of all numbers x in the universe such that, remember that vertical line means such that. So this curly bracket means we're looking at a set of numbers. X just says, it's just the notation that we use to say, we're looking at the set of all numbers such that x just isn't equal to -3 or 4. That notation right there is fairly abstract. You know, I would say most people, if they just kind of took a glance at that, they would say, what? Like, what does that notation mean? So what does that notation mean? What are we talking about? What's the best thing we can do right now? Yeah, draw a number line. Drawing a picture is always the best first thing to do. So what are we saying? We want to consider all the numbers in the world except -3 and 4. So what should I draw? -3 and 4. And what we're saying about -3 and 4 is that I'm not equal to it. So what symbol should I use? An open circle or a closed circle? Yeah, 2 open circles. But I am saying I'm allowed to be any other number in the universe. So we shade everything else. Yeah, very good. So we're shading everything else. And then what number goes all the way to the far left? -infinity. And all the way to the far right, +infinity. And now we have how many intervals? 3. And now this is going all the way back. Joseph, you mentioned the union symbol. We use the union symbol to write all of these together. So again, if you wanted to send an email to a friend with this solution, because I know you're all emailing your friends about intervals and number lines, but if you did, this would be hard to send as an email. Whereas what you could type in is parenthesis, -infinity, comma, -3, parenthesis, and then union. So that's the first interval. Next interval from -3 to 4, union, and then the next interval from 4 to infinity. So even though I started class by saying that interval notation is the lazy person's number line, which is true, it's also how you'd communicate in the 20th century. Like if you want to type these things down on a paper or send it an email or submit an answer into the Moore system, that's how you do it. Okay, and I think that the next one is fairly similar, number 8. I don't think we need to do that one together as a group, but you still need to go ahead and do it yourself. So how about everyone take a moment and do number 8. Go ahead and make a number line, jot down the relevant numbers. What is plus or minus for? That means both of them. You have to put +4 on the number line as well as -4 on the number line. Draw your number line, and then go ahead and start building your interval. I think I do. Yeah, that's what's your number? Art. Okay, very good. I'm not talking. Well, that makes me feel better that I wasn't just a dummy, that I didn't know how to do it. So something's just not working now. Yeah. Okay. All right. Sure. All right. Well, thank you, sir. No biggie. We can just watch some other time. Curious. I'll leave this back. No problem. Yeah, 1, 2, 3, 4 intervals. That's right. Good. Yeah, very nice. Yeah, start by drawing it on one. Great. Great. You like it? Okay, well here, and you definitely have all the numbers in there. And you can shape one circle and all 3. And then you're shaping everything else. So shape the left. And shape the right. Then it's important to always put like things on those things. That gives you the number that goes on that part. So now what we have is that's from that negative. So one interval is negative, next interval is 0. So give that a shot. Okay. Okay. Good. Let's go. Yeah. Let's go. Have you seen this stuff before? Oh, good. Okay, well, this is good review. Very nice, by the way. Oh, looking good. All right. Sorry. Can I see everybody's? Nice. Okay, so just so we all see the solution together, we'd have your number line, you'd put down 0, 4, and -4, and open circles on all three of them. We're saying the x can't be equal to any of those numbers, but we would shade everything else, and it's always important to put on your negative infinity and your infinity on the other side, and that gives you how many different intervals? Yeah, one interval here, one interval here, one interval here, and one interval here. And so we would say from negative infinity to -4, union from -4 to 0, union from 0 to 4, union from 4 to infinity. All right, well, now, so we're all done with interval notation. We're about to move forward and look at something else. Right now, you might be thinking to yourself, so, right? So, like, what is this skill even for? So, what is this skill even for? Yeah, it's about identifying points on a number line. And let's remember, what does shading mean again? Yeah, shading means included. Shading also means truth. Yeah, so what we're saying is that all these shaded values that we're talking about represent truth about the problem that you were just doing. These are potential solutions to the problem that you were doing. So shading means you're shading all the numbers that you're including in your solution set. They represent truth in your solution. And writing it down like this is just a fast way to write down your solution. And then to be able to communicate that information to another mathematician. It's just how we do it. So more than anything, I would say this is just a language of communicating your solution. It's not the solution itself. You still have to go through this whole process of solving for x and doing whatever you need to do to solve the problem. But this is how you represent your solution. Any thoughts or questions before we move on? All right. Well, then let's do it. I had a video that I wanted to show you real quickly, but there's no volume. Isn't that sad? I'm sad. I was really looking forward to it. So instead, and let's just see here. Do you think that it could just be like the website? Do you think that maybe if I used a different web browser, it could work? Is anyone with me on this optimism? Or am I just being silly? Let's just see what happens. Because obviously that didn't work, and IT guy couldn't do it. Nope. All right, oh well. Well, I'll show it to you next time. What I wanted to do was introduce you to a philosopher by the name of Descartes. Have you heard Descartes before? The philosopher's name, Descartes? Maybe you have, maybe you haven't. But you will recognize him, I think, from a variety of details about him. So first of all, go ahead and scroll down to the next part of your notes where it brings up the Cartesian coordinate plane. So the Cartesian coordinate plane is this thing. That's it. It's just the XY axis that you've been using all your life. That is called the coordinate grid, or you can call it the coordinate plane, or you can call it the Cartesian coordinate plane. In any case, the Cartesian coordinate plane is named after René Descartes. René Descartes. And he was a philosopher, a French philosopher, in, I'd say, the end of the 1500s. In fact, I think he died in the 1500s. So we'll just say roughly the 1500s. And Descartes was known for a few things. One was popularizing the use of the XY axis. So that's one thing he did. So just imagine, before him, I mean, people may or may not have been using it sporadically. He didn't invent it, but he popularized it. He wrote a book about it, and after him, everybody started doing it. So that's why it's named after him, because he eventually started the practice of using a graph, an XY axis. He also said, cogito ergo sum. Have you heard that one? Anybody? Cogito ergo sum? Maybe you have heard it in the English, because that's Latin. The English is, I think, therefore, I am. So that was Descartes. He wrote many philosophy books. He wrote many math textbooks. And one of his philosophical ideas that really caught on was this whole notion of I think, therefore I am. And I don't want to give it away too much because that's what the video is going to do. So I'm just going to leave it there. Okay, so that's just a little smattering so that you're familiar that there was a person who kind of started this whole thing, and it's named after him. So you can see here, Cartesian coordinate plane. Cartesian, where does the word Cartesian come from? Yeah, just the Cartes part of Descartes. So there we have it. So you have this grid. There's not too much I want to say about it because I think that we're all familiar with the XY axis and how to use it. Let's see here. Oh, yeah, I did say write some notable facts about it. So important facts. We write coordinates by using, you can just kind of write these notes on the page somewhere. We write down coordinates as x comma y, right? And so the x is representing the number on the x-axis, the y is representing the number on the y-axis. X, y, that's just one way to say it. You could also call this input-output. And what we're referring to here is when you have a function, which we are going to get to, let's say you have a function like the function f of x equals 2x plus 3. Then when you're dealing with a function and you input a number, let's say that I input the number 5. So then I would put 5 into the equation, so that's 2 times 5 plus 3. That's 10 plus 3 is 13. I now have an input and an output. And technically speaking, what that means is that if I graph this function on a graph, the coordinate 513 will be on that graph. And so whenever you use a function and you plug in numbers and then you see what it equals, input, output, each of those input-output pairs is on the graph. And I might as well take this opportunity to show you a really great website that will refuse what we will refer to over and over, which is Desmos. Has anybody used Desmos before? Desmos. If you just type in Desmos into Google, it's the first link, Desmos. And it's a really great graphing calculator. It's really great because as you start typing in your numbers, like 2x plus 3, it automatically starts graphing. And there we have it. So there's your nice graph of 2x plus 3. And what you'll notice is that if you go over to 5, there it is, 513. So that is the coordinate that I said would be on the graph. Sure enough, it is on the graph. And that's because it represents an input-output pair of numbers that you typed into the function itself. So just wanted to make sure you saw that 2 different ways of thinking about a coordinate. A coordinate is indeed simply x, y, but it's also representing the input-output of a function. Okay, I think that's really all there is to say about the coordinate grid. We'll continue to use it throughout class. Yep. So I believe this is the last concept in section 1.1, and that is the distance formula and the midpoint formula. Oh, I guess I'm done with this middle board now. So up at the top of your page there, you have the distance formula and the midpoint formula. Other than just using it to solve problems, I'd like to make sure we all see where that comes from. So take a note. Notice that these formulas are easy concepts in disguise. So when you look at the distance formula, which I think that you've probably all seen at some point in your life, you've got the big square root of x2 minus x1 squared plus y2 minus y1 squared. What is that formula? Like just looking at it, does it remind you of anything else? Yeah, thank you, Richie. The Pythagorean theorem. It is the Pythagorean theorem. And what I'd like everybody to do is draw on this diagram with me as we see how to derive that formula. It's worth seeing this at some point in your life in case you haven't already. So on that diagram, what we have is 2 points in space. So I have 1 point P, which is the coordinate x1, y1. And then I have another coordinate up here, Q. And that's the coordinate x2, y2. And the question is, how far is the distance between them? That's what we're trying to calculate, is the distance between any 2 points in space. Obviously, you could bust out a ruler and measure it that way, but we want to do it mathematically with precision. And so what you do is you draw a right triangle to connect those 2 points together. And then the first thing you do is find out how wide is the triangle and how tall is the triangle. So how wide is the triangle? If you look at this coordinate and this coordinate, this has the x coordinate x1, this is the coordinate x2. How far is it from x1 to x2? Like if I were to look at a regular number line and I start here at x1 and I move over to x2, that's how wide this triangle is. How do you calculate distance between two numbers? It's probably easier to look at actual numbers. How far is it from 3 to 8? Is it 5? How do you know that the answer is 5? You just subtract, right? You just do 8 minus 3. Likewise, over here, how do I know how tall this triangle is? My first y-coordinate is y1, and then my top y-coordinate is y2. How far apart are they? And again, it helps to have some numbers. So how far apart is 2 all the way up to, say, 11? What's that distance? Yeah, 9. And how do you get it? You just, you subtract. So you subtract top minus bottom. So in general, if we want to now go ahead and say how wide is this triangle, how tall is this triangle, you would simply subtract the two x coordinates, x2 minus x1, and you'd subtract the two y coordinates, y2 minus y1, and that's going to tell you how wide and how tall it is. So everyone, let's do that together. Go ahead and I want you to label how wide the triangle is right now, and you're going to label it with the width of x2 minus x1. So the width is x2 minus x1. And then what was the height? The height was y2 minus y1. So you just label that onto your triangle. Well, great. So now we know how wide the triangle is. We know how tall the triangle is. What we're really interested in is the length of the hypotenuse. So let's just call that d. And what we have now is just a triangle. It's a right triangle. And we can use the Pythagorean theorem on it. So the Pythagorean theorem, we know, is a squared plus b squared equals c squared, where you're looking at a right triangle whose sides are a, b, and c. And so we're just going to go ahead and plug in our values. So go ahead and write this down. Just find some white space on your page to do it. Although, to be even better, let's write it backwards. Let's write c squared equals a squared plus b squared. And then let's plug in our numbers. C represents the hypotenuse, so that's d. So everyone, you can write down d squared. And then A represented in our diagram the width leg, so that's x2 minus x1 squared. And then B represented the height leg, so that was our y2 minus y1 squared. And so now we've used the Pythagorean theorem to come up with an expression that has d in it, which is what we want to solve for, the distance between the 2 points. And it includes the coordinates that we were given. So the last thing is, how do we solve for d? D is being squared, so we need to square root both sides. So if we square root both sides, we end up with, voila, the distance formula. Now, you might say, Mr. G, I was perfectly content going through my life without seeing the derivation of the distance formula. I don't think I needed to see that. But nevertheless, wasn't that nice? That's how you derive the distance formula. What is the distance formula inherently? It's just the Pythagorean theorem. So that tells us that in general, when you want to find the distance between 2 points, like we're about to do it, we want to find the distance between these 2 points, you actually have 2 options. You could use the distance formula, or what could you do? You can just graph it and do the Pythagorean theorem. But we'll do both ways. So let's do one of these problems both ways. And I say, let's go ahead and start off with number 1. Let's do the distance formula. So right there below number 1, let's start by drawing a nice graph. So I've got the coordinate 1, 2, the coordinate negative 3, 5. And by a nice graph, I mean try to really make it nice. So we're going to do tick marks, just the tick marks we need. So the coordinate 1, 2, right there. And then the coordinate negative 3, left 3, and then up 5 is right here. And we'd like to find the distance between those 2 points. So on the one hand, we could go ahead and use the distance formula. That's one option available to you. You could label these coordinates as you could label these coordinates as x1, y1, x2, y2, and start plugging it into your distance formula. You could do that. Or you could go ahead and draw this right triangle below those 2 points and do the Pythagorean theorem. So from your graph, can you tell how tall is this triangle? If you did all your tick marks, you should be able to look at your graph and see. Is it 1, 2, 3 units tall? Everyone look at your own picture and convince yourself. 3 units tall. So the triangle is 3 units tall. How wide is it? Again, you can just count your tick marks. If you did tick marks, you're starting here and you're going 1, 2, 3, 4. Is it 4 units wide? So we have a triangle here that is 3 units tall, 4 units wide. And now you can just do the Pythagorean theorem. We'll call the hypotenuse d for distance. And we go ahead and do the Pythagorean theorem. Leg squared plus leg squared equals hypotenuse squared. Although, again, sometimes it's more fun to write, not more fun, but c squared equals a squared plus b squared. Since we're interested in solving for c, which is hypotenuse, you can write it backwards. C squared equals a squared plus b squared. So what do we get? D squared equals a. Now, which one of these is a?
Technically, it wouldn't matter because the formulas.
Yeah, technically it doesn't matter. You can use the height or the width. It really doesn't matter. You can switch them around. So we'll just say 3 squared plus 4 squared. And so that gives us d squared equals 9 plus 16, which is d squared equals 25. And again, d is being squared, so how do you solve for d? Square root both sides. And we end up with d equals 5. So there's our distance between those 2 points. Now, let's also now go ahead and do the distance formula to try that out. So the distance formula, now, whenever we use a formula, there's a best practice. And the best practice is first, write the formula. I know that's probably shocking. First, write the formula. And notice that it's either x2 minus x1 squared plus y2 minus y1 squared. Or you could just as easily write x1 minus x2, y1 minus y2. That doesn't really matter. Just so long as the numbers are consistent, 2, 1, 2, 1, or 1, 2, 1, 2. So there's our distance formula. Write down the formula. Then what you do, and I'll say this a lot in this class, you write it empty. You write the formula empty. Now what does that mean, to write it empty? It means you're going to write it down with all the structure of the square root, the minus signs, the parentheses, the squares, the pluses, but you don't put any numbers in yet. So check out how I do it. The square root of parenthesis something minus something, parenthesis squared, plus parenthesis something minus something, parenthesis squared. It's called writing it empty. You can see the structure of the formula is there. That's everything that the formula is telling you to do. You've got to subtract those numbers, then square them, subtract those numbers, then square them, and then add them, and then sort of the whole thing. We just didn't write any numbers in yet. And now this is really handy because visually, your eyeballs now, because you wrote the formula right on top of each other, it's very easy to go get the numbers and plug them in. So for instance, what's x2? Yeah, -3. And then what's x1? 1. And what's y2? 5. And what's y1? 2. So that's called writing it empty and then plugging in the numbers. And that's always the way I'll do it, because it's a best practice. You're making sure you have the structure of the formula correct, and then you're putting in the numbers carefully one at a time. So now what do we have? We have -3 minus -1, or sorry, -3 minus 1 is?
-2 squared. Oh, sorry, it's plus, and then it's a -4 squared.
Yeah, -4. Now, folks, this is important. You've got the whole problem hinging upon these, addition and subtraction facts with negatives. So I would encourage you to maybe double check your work on your calculator, unless you feel very confident about adding and subtracting positives and negatives. It never hurts, you have your calculator on. So this is the -4 squared, and then 5 minus 2 is 3 squared. And at this point, notice what the formula just gave us. What do you notice about the 4 and the 3?
It's the same.
Yeah, that's the legs of the triangle, which is just one more reminder that the distance formula is nothing other than the Pythagorean theorem. And so these numbers, the x2 minus x1, y2 minus y1, those actually represent the legs of the triangle. I realize the -4 might seem confusing, like, hey, that's not -4, that's a 4. But what happens when you square a negative? It's positive anyway. So there we have it. The distance formula also gave us 16 plus 9, which is the square root of 25, which is 5. Okay, so my question to you is, which do you like more? You like the Pythagorean theorem, Josh? Yeah, I like it too. And who likes the Pythagorean theorem method? Who likes the distance formula method? Some of you? Yeah, I mean, both work. And to be honest, I'll give you credit either way. So on a test, if you had a distance formula problem to do, I would give you credit either way. You just have to show some sort of work. All right, so everybody go ahead and try number 2. In number 2, the first thing you might notice is, and so again, you can do number 2 however you want to do it. You could do the Pythagorean theorem, you can do the distance formula. The thing is, if you do the Pythagorean theorem, notice these coordinates, 3, -10, like, there's a lot of tick marks, right? This one was easy because there weren't that many tick marks and it was simple. But as soon as you get to coordinates that are kind of bigger, you need to be very careful about counting your way from one coordinate to another. And that demonstrates the downside of the Pythagorean theorem, is that in order to do this method, your drawing has to be good enough that you can actually read how tall the triangle is and how wide the triangle is.
It would be better to do it.
Right, maybe. I mean, maybe since the drawing is a little bigger, maybe that'd be better to do the distance formula. It's really just comes down to your own comfort. But I mean, now that I've drawn all my tick marks, I absolutely can just count my tick marks. How tall is it? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Anyone else get 12? And then how wide is it? I go back to my tick marks. 1, 2, 3, 4. So it's still possible. You can do the Pythagorean theorem. Your drawing just has to be good enough to support your ability to look at those details. So choose one method or the other. Let's see. Either way, it's 91. And you're going to do -10 minus 2, or you can do 2 minus 2. Or those 2. So let's just look. If you're going to subtract in the order of 91, that means there's 20 from that, right? -1 minus 2. So now you do 2 minus 10. Which if you have 10 minus 10, you take it plus. Right down, come over here like 2 minus 10. And what happens when you have a double negative? Exactly. So then that's 2 plus 10. Yeah. Yeah, that's step by number 4. This right here, you're doing 2 minus negative. Right, right. Okay. So, on the one hand, if you did the Pythagorean theorem method, you just have d equals, well, d squared equals 12 squared plus 4 squared, and then you go ahead and square those numbers out, so that's 144 plus 16. Right, am I doing that right? And then that's 160. And you square root both sides. Did anyone else get the square root of 160? Okay. Now, the square root of 160, that's a whole nother problem, which is that we can actually simplify that. But I think I'm going to have a particular lesson for us where we actually review how to simplify roots. So let's just leave that there for now. You can type it into your calculator and get an approximation for what that is. What would an approximate value be from your calculator? Is it 12 point what?
12.649.
12.649 roughly. So I'll just say 12.6. So the distance was 12.6. So if this leg is 4, that leg is 12, the distance between them was roughly 12.6. Yep.
Are you gonna have this one back?
That's a good question. What was the actual, how many decimals did you get?
It's 12.6.
49. So it really just depends on the problem. If you're working in money, then obviously you'd want to do cents. But if you're doing a problem like this, oftentimes 1 decimal is enough. Theoretically, the problem will tell you how many decimals to include. Especially like if you're online and you're on the More website, it'll tell you, almost always, it'll ask for 4 decimals of accuracy. So maybe we should just all agree as friends to always give 4 decimals of accuracy, because that's what the problem will want. So for instance, thank you, Chelsea, for asking this question. I'm going to do the square root of, the square root of 160 is technically 12.6491164, which, by the way, is an irrational number because the decimal is going indefinitely and there's no repetition. So if we want 4 decimals of accuracy, that would be the 6, 4, 9, and 1. Now, does that 1 get rounded up, or does it stay the same? Stays the same. So the answer on the More website would be 12.6491. But I'm pretty sure the More website would rather you just type in the square root of 160. Because keep in mind, the square root of 160 is the actual real answer. And if you type in 12.6491, it's an approximation. And you just lost all the rest of the infinitely many decimals of accuracy. On the test, you'd write your answer down as just a square root. Yeah. I'll try to be as specific as possible in the instructions on the test so you feel confident that you know what to do. And if for some reason I don't give an instruction, you can always just come up and ask me and say, hey, what do you want? Do you want a square root or do you want a decimal? Okay, now, if you did the distance formula method, what did you come up with? So first of all, I hope that you did write it empty. So you'd have parenthesis squared plus parenthesis squared. And then I hope that you did write down the coordinates and label them. So for instance, my coordinates are, hold on there, it's what, 3, -10. And the other coordinate is -1 and 2, thank you. And so now label it first. This is x1, y1, and x2, y2. And so now, if you provided you write the formula down on top of your empty one, so x2 minus x1 squared plus y2 minus y1 squared. Okay, so now I can just plug in all my numbers. x2 is -1, x1 is 3, y2 is 2, and y1 is -10. Now you saw the process I just did. As I walked around the room, there were at least a good handful of you who put these numbers in the wrong order. And so I'm not sure exactly why you put them in the wrong order, but this is why I recommend writing it empty, writing it blank, and having the formula right above it, and labeling it so that you're very, very, very careful as you put those numbers in. So now what do we have? We have the d equals the square root of -4 squared plus 2 minus -10. That's a double negative, so plus 12 squared. And at this point, we have the same solution, the 12 squared plus the 4 squared. Okie doke. Everybody, you can see number 3 was fractions. You can just cross that problem out. We've done 2 problems. I'm feeling pretty good about that. Now, would you have to do that whole problem with fractions, or what could you do?
Decimal.
You can just convert it to a decimal. That'd be pretty easy, 0.5 and 1.5. Okay, so that is the distance formula. What about the midpoint formula? Can you write, what concept is at play in the midpoint formula? It says x1 plus x2 divided by 2 and y1 plus y2 divided by 2. What do you call that when you add 2 numbers and divide by 2? Or what do you call that when you add 3 numbers and divide by 3? Or add 4 numbers and divide by 4? What are you doing when you do that? Yes, who said that? Yeah, Karis, that's the mean. And what's the more common word other than mean? It's just the average. So go ahead and jot that down. The midpoint formula is really just the average. So everybody now in your notes, you should say the distance formula is really just the Pythagorean theorem, and the midpoint formula is really just the average. You're just averaging the coordinates. So I say let's just do one of these. And in fact, I tell you what, we can go ahead and do number 3. Why not? Because it was there anyway. I realize you might have already crossed it out because I said to, but I'm going to go ahead and do it anyway. So we have 2 coordinates, and we'd like to find the midpoint. Now, on the one hand, since we want to find the midpoint of these 2 coordinates, you could still just go ahead and graph it. So how do I graph a half? How do I graph the coordinate half for?
Just estimate.
Yeah, you just estimate, right? Instead of going all the way at 1, I just go half the way. So one coordinate is at half, 4, and the other coordinate is at 3 halves, which is 1.5, 1.5. So that other coordinate is 1.5 down 1. And again, you're just estimating. You're putting it roughly halfway between the 1 and the 2. So those are my 2 coordinates. Now just kind of look at it with your eyes and kind of pinpoint with your finger, where's the midpoint? Does that look like the midpoint? Roughly speaking. So somewhere in there, I'm expecting my answer to be. I'm just going to kind of put a little circle here to say, well, that's visually the midpoint, so I better get an answer that falls in that area. So now let's do it. To do the midpoint formula, you just average the x coordinates and you average the y coordinates. So, again, always a good practice to write down the formula, x1 plus x2 over 2, y1 plus y2 over 2, and then label, this is x1, y1, this is x2, y2. And now we'll go ahead and just average them. So my x coordinates are 1/2 plus 3 halves, all over 2. And my y coordinates are 4 plus -1, all over 2. And again, what we're doing here is just taking an average. We're adding them and dividing by 2. So what's 1/2 plus 3 halves? Yeah, on the one hand, 1/2 plus 3 halves is 4 halves, which is 2. Or you can say 0.5 plus 1.5 is 2. Or 50 cents plus $1.50 is 2. So we have 2 over 2. Then over here, 4 minus 1 is 3. That's 3 over 2. And so 2 over 2 is just 1. And 3 over 2 is 1.5. That's totally fine if you want to put your answer as a decimal. And so is that where my answer should have been? 1, 1.5? If I go over 1 and go up 1.5? Yeah, that's where I predicted it would be. And in fact, that's where it was. Folks, whether you do the distance formula or the Pythagorean theorem, and when you do the midpoint formula, probably my biggest recommendation, and I will do it all day long when we're in class, is drawing a picture to support your work. Drawing a picture to support your work is really important because at the very least, you're getting an idea of what the answer should be, and then you're able to check yourself to see if it was accurate. Yep. Yes, sir, Joseph. Boy, that's a really good question. On the test, sometimes I might give you the formula, but other times not. But what I could do is at least give you a formula list so you know what formulas you would need, and then you can work on memorizing them, and that way on the day of the test you'll be better prepared. Yeah. Okay, well folks, let's turn the page, talk about relations. So, first of all, what's that? Almost done? Okay. So first of all, folks, recall the equation of a line. What is the slope-intercept form equation of a line? I think I might have just heard it, but I was erasing. What's the slope-intercept form of equation of a line? Yeah, y equals mx plus b. Go ahead and jot it down there on your paper. Y equals mx plus b. And now go ahead and take a moment, look at that formula, y equals mx plus b. You've been using it your whole life. And recall in your head, what does the m, x, and the b stand for? All right. So let's all take some notes together up there. You have the equation of a line, y equals mx plus b. And what does the m stand for? What is it? Slope. And then what does the b stand for? You have the y-intercept. Now here's a good one. What does the x and y represent? We don't normally talk about that. We just say, oh, m is the slope and b is the y-intercept. But what does the x and y represent? Yeah, they represent a coordinate on the graph. That xy literally is the xy of a coordinate. So let's just do an example here. Here's our graph again from Desmos. I'm going to do the graph of, how about 1? I'm going to do the graph 1/2 x minus 3. So here's my line. There we go. It's 1/2 x minus 3. So the slope is 1/2 and the y-intercept is -3. Sure enough, you can tell the y-intercept is -3. And then the slope is 1/2. That means it's going up 1, right 2, up 1, right 2. And it is. It's going up 1, right 2, up 1, right 2, up 1, right 2. So there's your equation. Now let's just check here. Here's a coordinate right there. If I can get it. Yep, there we go. What's that coordinate? 2, -2. So in this equation, where I've written down y equals 1/2 x minus 3, if I take the coordinate 2, -2, which we just saw was on the graph, what will happen if I plug that coordinate in for x and y?
-2 equals 1/2.
Yeah, let's plug it in. So the -2 is the y. I'll even label it x, y. So there's my -2, 1/2 times x, which was 2. And then what? Half of 2 is 1. And then 1 minus 3 is -2. Well, what did that just tell us?
It's the same.
Yeah, it told us -2 is equal to -2. Is that true?
Yes.
It's true. And in fact, that's what all equations do, is if you plug the valid numbers in for x and y or just x, you should end up with a true statement. And in fact, when you look at that graph, I had -1, 2, 3, and then I'm going up 1, right 2. Approximately, that's my graph. This line right here is really a shaded line. That's what that is. This whole line is shaded. It's a line. And what does shading represent again? True. So the x and y in this equation represents every single coordinate that is on that line. And any one of those coordinates on this line, if you plug it into the original equation, it'll give you a true statement. And so the whole line represents truth. It represents the truth of all the coordinates in the universe that you can plug into this equation, and it would make it true. And that's what the graph is. The graph is really just shaded. You're just shading in all the points that make it true. What happens if I choose a point not on the line? That'd be false. What if I chose the coordinate 1, 1? That's simple enough, 1, 1. If I plug that into the equation, so I'm going to do y equals 1/2 x minus 3, and I'll plug in 1 for y and 1 for x. Ooh, that gives me 1/2 minus 3 is -2.5. What's 1 equals -2.5? False. So one way to think about all graphs is that the graph itself represents truth, and what does every other point represent? Yeah, falseness. And that's what a graph really is. The graph itself, whether it's a straight line or a parabola, represents truth of what coordinates you can plug into the equation to make it true, and every other coordinate in space, it represents falseness, that if you plug that coordinate into the equation, it'd be false. Okay, so that's your notes to just kind of remind yourself about y equals mx plus b. I think that's all I wanted to say there. Give an example of each type of slope. So what can slope be? First, we might as well go ahead and jot down the definition of slope. What is slope? What's the definition of slope? What's the common definition of slope? Yeah, thanks, Jackie. Rise over run, right? Rise over run. That's typically how we talk about slope in textbooks. Is that how you learned it back in the day? Did you learn it any other way? No? Okay, so here's what I'd like us to think about. Rise is, well, first of all, rise is a bit of a misnomer. What does that imply you're always doing? Going up, but are you always going up? You're not. So instead of using the word rise, we use the word vertical, meaning that you're either going, you're making some sort of vertical movement, but you could be going up or down. And then run, well, what does run make you think you're doing? And I guess it means you're going right or left. And it doesn't mean you're going right or left. You don't really know. But instead of using run, we can say horizontal, because you know that that's a horizontal movement. So that's a slightly better definition of slope. But the best definition of slope that I'm going to use in class is slope is the up, down, over the right, left. And that is technically slope. It's talking about a fraction where the numerator tells you how you're moving up or down, and then the denominator tells you how you're moving right or left. And the more specific we are, the easier it is to interpret a slope. So up is positive, down is negative, right is positive, left is negative, and that's the definition of slope. I know my phone just went off. That means we're going to take a break, but I'm just going to wrap up this thought. So that's the definition of slope. Another definition of slope is the actual slope formula. Who recalls the slope formula? If you have two coordinates in space, x1, y1, and you'd like to find the slope between them, what's the slope formula? Yeah, thank you, Jessica. y2 minus y1 over x2 minus x1. Okay, so there's the slope formula. So these are all some technical things we need to know and remind ourselves. And then finally, give an example of each type of slope. This is simple enough. Slope can either be, what's that slope? Positive, slope can be negative, slope can be, what's that slope? Now this is 0, whereas what's this slope? Undefined. Okay, so those are the 4 basic types of slope. So what that tells us is that when you use the slope definition of the slope formula, it's going to spit out a number that's either a positive number, a negative number, 0, or if you did this formula on your calculator, the calculator would give you an error message because it's undefined. And that tells you that it's vertical. So a horizontal line has 0 slope, and a vertical line has undefined slope. Yep, and that's a good stopping point for us to all take a break. So the time is 9:02. Let's all be back in the room at 9:12. Remember, the only rule about break time is you have to leave the room at least once. You have to get up, help the blood pump its way back to your brain, and then you can come right back in. Hey, Chelsea. Oh, all right. If you're still in the room, could you bring up your syllabus quiz and your personal info sheet? I'll just throw a little stack right here. Thank you.
major cuts and kind of relieve the pressure of those two trees on how they're both growing drastically toward your house versus straight up. Like we kind of talked about. So just think about that. If I just did the front, and if I just did the front yard, and the front tree, it's $450. And for just a total of $550, which is just $100 more, I kind of tidy up those two surmounts in the corner for you. That's kind of thinking that I try to help you with it. So keep that with it. But I'm not I'm an honest fan. But of course, I have a family. I got to take care of too. I don't have expenses. Let's try to be straight. So just remember that $450 for the front tree, but it's only a total of $550. Call back or text me if you can. Everybody? Right now it's Wednesday at about 8:45. Have a great day. Tom's work 602-435-8837. Bye-bye.
Pretty much the same.
Thanks, sir. Folks, as you're coming in, if you didn't already bring up your syllabus quiz and your personal code sheet, please bring it up. Oh, but this time, you're going away. All right, let's continue. If you didn't already bring up your student info sheet, your syllabus quiz, you can just drop it by right at the end of class. So, this next section, it tells us the equations of vertical and horizontal lines. So let's just clarify why we would need to know that. First of all, let's say that you had a positively sloping line. That would be something like y equals positive 1/2 x plus 2, for instance. The slope is positive, so it would just be normal y equals mx plus b. What if you had a negative sloping line? Then you'd have something like y equals negative 2/3 x plus 4. And again, negative sloping line, negative slope. So what would the equation be for a horizontal line? What is the slope? 0. So if I plug in y equals mx plus b, and I put a 0 in for m, what's 0 times x? Just 0. And then 0 plus b is just b. So what we have here is that the equation for a horizontal line is simply y equals the y-intercept. So that's the first thought. Everyone now, let's take a look here at number 2. We'll do number 2 first, all right? So when you look at number 2, it says identify each equation as either a horizontal line or a vertical line. Well, the first thing that we want to know for this problem, y equals 3, just remind yourself right here that when you have y equals mx plus b, and if m equals 0, because it's a horizontal line, then the equation simply becomes y equals 0x plus b, which is just y equals b. So that is the equation of a horizontal line. And I hope that makes sense why that's true. Because we're saying a horizontal line, which is like this, the slope is 0, and therefore the mx term goes away, and it's just y equals b. So this problem right here is y equals 3. What does the 3 represent? The b, the y-intercept. So this means y equals 3, let's go ahead and draw it, is a horizontal line whose y-intercept is 3. So you can go ahead and go up to 1, 2, 3. There's the y-intercept. And what kind of line do you draw? Yeah, just straight across a horizontal line. So this is important that you're able to just quickly visually recognize that if we say y equals 3, that's just a horizontal line. Now you might ask yourself, well, other than the fact that y equals 3 is just y equals mx plus b, where the mx term went away, so it's just y equals b, what do you know about every single coordinate on this horizontal line? Like, let's just go ahead and write in some coordinates. This is the coordinate 0, 3, and 1, 2, 3, 4. This is the coordinate 4, 3, and then 5, 6, 7. This is the coordinate 7, 3, and then if I go to the left, I'm going to 1, 2, 3. This is the coordinate negative 3, 3. What do you notice about all those coordinates on that horizontal line? Chelsea?
The y coordinate is always the same, and the x coordinate can be an infinite number and a number positive.
Right, yeah, the x coordinate could be anything, but the y coordinate is always 3. And that's literally what this equation is telling us. Y is always 3. This is basically saying, think of every coordinate in the universe with y equals 3. So where is every coordinate in the universe whose y value is 3? Right here, on this horizontal line. Every coordinate on that line is going to have a y value of 3, and therefore y equals 3 represents a horizontal line. So let's now do number 1 and run that reasoning the same way. If y equals 3 or y equals b represents a horizontal line, what would x equal a number represent? A vertical line. And so we could go ahead now and just say this is a vertical line. And let's go ahead and graph it. Now, if this was y equals the y-intercept, which is not a bad way of representing it. Instead of y equals b, you could say y equals the y-intercept. And therefore, if it's y equals the y-intercept is a horizontal line, what's the equation of a vertical line? X equals, if it's y equals y-intercept is a horizontal line, it's x equals x-intercept. So that's the equation of a vertical line. It's just x equals the x-intercept. So in this case, our x-intercept is negative 2. So we go on over to the x-axis at negative 2. And then what do we draw? Just a vertical line. And again, what's the slope of a vertical line? Undefined. So x equals 2, x equals negative 2 represents a vertical line the slope of which is undefined. And again, how can we kind of make sure in our head that this makes sense? Just look at a variety of coordinates on this line. This coordinate right here is -2, 0. And if I go down 3, this coordinate right here is -2, 3. And if I go up a bit, then this coordinate right here is -2, 4. What do you notice all of these coordinates have in common? Yeah, the -2 is the x value, which is literally what we're saying. We're saying think of every coordinate in the universe whose x value is -2. And if you looked at every coordinate in the universe whose x value is -2, you'd be looking at all these coordinates that are stacked on top of each other in a vertical line. Chelsea?
Wouldn't your coordinates for -2 be -2 and -3?
Yes, they would be. Thank you very much. Okay, so there we have it, folks. The equation of a horizontal line is y equals the y-intercept. The equation of a vertical line is x equals the x-intercept. We use that fact a lot. Okay, now we get into the good stuff, folks. And now, obviously, it's all good stuff. But, you know, the first day or two, we were talking about number sets like rational and irrational, and then we did interval notation, which is just a way of representing a solution. Now we're going to talk about actual solutions. How do we find and solve problems and make graphs? There we go. So, graphs of equations, here we are. It says the fundamental graphing principle is the graph of an equation is the set of points which satisfy the equation. And that, in fact, is what we already said. I already erased it. But when I said y equals mx plus b, and we said, what did the x and y represent? What did the x and y represent? Coordinates. Coordinates that are on the line, coordinates that are on the graph. And specifically, if I plug a coordinate on the graph into the equation, it will make the equation true. So that's what they mean here. The graph of an equation is the set of all the coordinates that make the equation true. That's one paraphrase. Just kind of jot that off there. A graph is simply a set of coordinates that make an equation true. So just to kind of make this fun, let's say that I go into Desmos and I make myself some sort of a really strange formula, like x. So let's say we had x squared minus 3x plus 4, and then all of that gets divided by the square root of x, and then maybe minus 3. There we go. All right, well, that's kind of an interesting looking graph. It's not quite a parabola, is it? It's like a parabola that's leaning over to the right. Maybe it got imbalanced and it's falling over. But so there we have it. There's a little equation there. Oh, and that's because I put 3 inside the root. I put the outside the root. Oh, that's not very exciting. Let's try this again. How about x minus 2? There we go. That's a fun graph. Okay, so we have some interesting looking graph here. And I have an equation here that I wrote down. The equation is not all that bad. The equation is just x squared minus 3x plus 4 over x minus 2. And I'm just going to arbitrarily come over here and choose a coordinate. Well, they're all decimals. I don't know that any whole numbers are going to pop up right here. Well, let's just look at that coordinate. 8.6 and 7.903. It's not exciting in and of itself. Yeah, Bryce?
No.
Oh, yeah, okay. But what would happen if I plug in 8.6 for x? Hold on. Let me jot this down now. So I came up with this crazy equation, x squared minus 3x plus 4. And I put over x minus 2. And I'm just choosing some random coordinate from the graph, which I already forgot. 8.54.
It was 8.6.
So 8.54. And what was it? 7.846? Did I do that right? Was that the number? It's not critical that we have it exactly right. The point is, what happens now if I plug in that for x and that for y into this equation?
It should become a true statement.
Yeah, it'll be a true statement. It won't be an interesting true statement. It'll simply be true. It'll boil down to something like 7.846 equals 7.846. And that's the key behind all graphing, is that every graph you'd ever look at, if you take any coordinate, so you can just choose any coordinate from the red line, any and all, and then plug that coordinate into the equation y equals that, it'll make a true statement. And that's what your notes say, right up there at the top, the fundamental graphing principle. All right, we'll just keep going. The next thing it says is x-intercepts and y-intercepts. So we'll use this definition. An x-intercept is a point where the graph intersects the x-axis. Let me just go ahead and show that. And a y-intercept is a point where the graph intersects the y-axis. So on my graph here, do I have a y-intercept? Yeah, there's my y-intercept. Do I have an x-intercept? I actually don't have an x-intercept. My graph never touches the x-axis. But maybe if I just shift the whole thing down a little bit, like that, now do I have some x-intercepts?
Yes.
Yeah, there's one, those are my x-intercepts, and that's my y-intercept. So what we're going to learn is how do you find those intercepts? Obviously, if you graph it, you can just look. But how do you find it algebraically without looking at a graph? And in fact, that is what this next section is going to tell us. Finding the intercepts of a graph, given an equation x and y, find the intercepts as follows. Now, this might not look very clear. It says x-intercepts have the form x comma 0, set y equals 0 in the equation and solve for x, or y-intercepts have the form 0 comma y, set x equal to 0 and solve for y. I'd like you to take some notes right over here. Take a note with me, and I'd like to make it a little more clear. When you have a graph and you have a function, whatever that function may look like, so that's our f of x, then this right here is a what? It's an x-intercept. So there's my x-intercept. And then this right here is y-intercept. Okay, so now algebraically, how do we find these things? Well, an x-intercept is a coordinate that looks like this, x comma 0, right? Because you've moved to the right x units and you didn't go up or down, so you're right there. And what this tells us is that in order to find an x-intercept, this is our function, you want the function to be equal to 0. Because a coordinate, I should say this, x comma y can also be written as x comma f of x. Because just in that formula that we just did, the y equals x squared minus 2x plus 3, I'm not writing that the exact same thing. But y equals all that could also be written as f of x equals. So just so everyone knows, f of x and y are synonymous. Whether you're saying f of x is equal to that function or y is equal to that function, y and f of x mean the same thing. So as you go through life, you could either write down coordinates as x, y, or you can write down coordinates as x comma f of x. It means the same thing. So if you want an x-intercept, we're saying that the y value is 0, and if the y value is 0, you're setting f of x equal to 0. So if you want to find an x-intercept, you set f of x equal to 0 and solve. That's your method for finding x-intercepts. You set the entire function, whatever equation they gave you, equal to 0, and you solve. Whereas a y-intercept is of the form, say, 0, 1, like for instance, 0, 6. And in that case, what we know is that x is equal to 0. And so if you'd like to find a y-intercept, all you have to do is let x equal 0, which means plug in 0 into f of x, which is simply f of 0. And you plug 0 into the formula, and it will tell you the y-intercept. Now that's all just on a diagram. If you wanted to just write it down, you could say a y-intercept, to find the y-intercept. To find the y-intercept. Plug in 0. So you're going to find f of 0. To find the x-intercepts, set f of x equal to 0 and solve for x. This is the technique we'll be using. So anytime you want to find a y-intercept, you just plug 0 into the equation and it will tell you the y-intercept. Anytime you want to find the x-intercepts, you have to set the entire equation equal to 0 and solve for x. That part is a little more lengthy. So let's go ahead and give it a shot. Try this out. And so let's see. That's the example. It says for each equation, find the x and y intercepts, create a table of values, and sketch the graph. Okay, we can do that. So let's do this example. We have our equation, y equals negative x squared plus 9, which, go ahead and write it down in your own handwriting. You can also write down as f of x equals negative x squared plus 9. Because y and f of x are truly synonymous. You can use them interchangeably. So we have this function. Let's do the easy one first. How do we find the y-intercept? Yeah, you just plug 0 into the function. So if I plug 0 into that function, f of 0 is negative 0 squared plus 9. 0 squared is 0, negative 0 is still 0, plus 9 is 9. And therefore, the y-intercept is just 9. We'd like to write that down as an actual coordinate. That tells us that x is 0, y is 9. What coordinate is that? If x is 0 and y is 9, the coordinate is?
Parentheses 0.
Yeah, 0, 9. So there's our y-intercept. And I'm going to start a graph here. My y-intercept would be, there's my y-intercept so far on my graph. Now let's find the x-intercept. To find the x-intercept, what do? To find the x-intercept, yeah, we set f of x equal to 0 or y equal to 0. What that means is you take this whole equation here and you literally just set it equal to 0. So I'm going to write down negative x squared plus 9 is equal to 0. And now you have to actually do some algebra. So you can see this first process is very easy. Plugging 0 into an expression is always easy. Whereas setting an expression equal to 0 means you're about to do some algebra. So how do we go about solving for x now? We've got x being squared multiplied by a negative 1 and adding 9. How do we start solving for x? Yeah, we need to get x by itself. Would everybody start by moving the 9 over? I think that's a pretty good start. So we move the 9 over. So now we have negative, I'm going to write negative 1 times x squared. Anytime there's a negative in front of a variable, I like to put a 1 there just so I can see it more clearly. Okay, so now I have x is being squared and multiplied by negative 1. What do I do next? Divide off the negative 1. Now we have x squared equals 9. Yeah, so x is being squared, so we square root both sides. Now, what happens when you square root a number in the process of algebra? Is it just 3? Yeah, it's plus or minus 3. When you square root a number in the process of algebra, you actually do the plus or minus. So that means there's 2 different x-intercepts. There's one x-intercept at 3, and there's one x-intercept at negative 3. So now I'm going to go to my graph again and go 1, 2, 3. There's one x-intercept, 1, 2, 3. There's another x-intercept. Oh, and I would like to represent these as coordinates. The x value is positive 3 or negative 3. What's the y value of the coordinate? 0, because we were setting y equal to 0. So my 2 x-intercepts are negative 3, 0, and 3, 0. Okay, so just looking at that, can you tell what the graph looks like? Keeping in mind that our original equation was negative x squared plus 9, what's the shape of an x squared graph?
Triangle.
Not a triangle, but a parabola. Yes, and plus there's a negative sign in front, so is the parabola facing up or is the parabola facing down? It's facing down. And in fact, now we can all see it. There's our parabola. Take your pencil and just kind of trace through. There's your graph. Just to show it, here is the equation negative x squared plus 9. Oops. Plus 9. Yep. There we go. So did we get the same thing as what the graph shows? We sure did. And you'll notice the y-intercept is at 9, the x-intercept is at 3, and at negative 3. So that's our process. Let's try that again now with a variety of problems. So now, as we move forward here, I would say that this is going to be some meaty review of algebra that you've done in the past. And let's just read our instructions here. It says, for each given equation, find the x and y intercepts, and then create a table of values, and then give a sketch of the graph. So let's begin with number 1. We have y equals x squared minus 2x minus 8. Now with any graph, or I'm sorry, any function you ever write down, you might begin by asking the question, what does that look like? Like, what does the graph look like? Any guesses on what the graph looks like? Because there's an x squared term, it should be a parabola. It should be a parabola. And it's positive, so should the parabola be facing up or down? Facing up. So we've got some sort of parabola facing up. That's all we really know for sure right now. So now let's go ahead and start the process. We're going to find the x and y intercepts. And again, I just want to show this again. Anytime at all that you want to find, you have some function, and you want the x-intercepts and you want the y-intercepts, with the x-intercepts, you set f of x equal to 0. With the y-intercept, you just plug 0 in for f. So this is a very condensed picture to remind you of your techniques. The x-intercept means set the equation equal to 0 and solve. This is algebraic. This is hard. Whereas here, the y-intercept, you just plug 0 into the function and simplify. This is easy. So this is arithmetic, which is simple. This is algebra, which requires a couple steps. So which one should we start with? Yeah, do the easy one first, right? I mean, why not always just do the easy one, give yourself a good positive feeling like, hey, I'm halfway done with the problem. So let's find the y-intercept. The y-intercept, you simply plug in 0 into the function. Now for that, I'm going to remind myself this is really f of x. So f of 0 then, in that case, means plug 0 in everywhere. So that's going to give me 0 squared minus 2 times 0 minus 8, which is 0 minus 0 minus 8. Now again, notice, your input was an x value, and your output is a y value. Input, output. Therefore, what does the 0 and the negative 8 represent? A coordinate. So what we have here is our coordinate 0, negative 8. That's our y-intercept. Okay, x-intercept. The x-intercept is the one where you have to set the entire equation equal to 0 and then solve for x using algebra. This one's going to be a little more time-consuming. So let's set our equation, x squared minus 2x minus 8 equals 0. How do we solve that? X. Well, you could add 8 to each side, but I don't think that's going to help us get towards the answer. When you have a quadratic, there were a variety of techniques that you've learned at some point about how to solve them. One technique is to factor. Another technique is to use the quadratic formula. Another technique is completing the square, but we wouldn't do that in this case. So what should we review, factoring or quadratic formula? Well, I kind of heard both. Let's do factoring first. So folks, remember factoring, we want to rewrite this as two binomials being multiplied together, where we have an x and then some other two numbers, and that's called factoring. The way you do factoring is you look at the last number and you say, what two numbers multiply to make negative 8 that add to make negative 2? So what two numbers multiply to make negative 8 that add to make negative 2? Let's try it. Here's a factor table. To multiply to make 8, it's either 1 times 8 or 2 times 4. Those are the only possibilities. I can do 1 times 8 or 2 times 4. But I need to multiply to make a negative 8, which means that either one of these is positive and one of them is negative. So thinking of all those possibilities, either, I could write them out, a negative 1 times positive 8, or a 1 times a negative 8, or a 2 times, negative 2 times a positive 4, or a 2 times a negative 4. Do you agree that's the only ways to multiply to make negative 8? Okay, so which one of those adds to negative 2? Yeah, 2 times negative 4. So those are the numbers. When you ask the question, what numbers multiply to make negative 8 that add to make negative 2? The numbers are 2 and negative 4, and therefore your factoring is 2 and negative 4. Okay, so there we go. We just factored the expression. And what does that do for us? Now that it's factored, we still want to solve for x. Do what, John? Well, wait. I mean, it is possible to simply look at this and know that these numbers now represent your x coordinates. But what we do now, so this is a review of factoring, which you have spent time doing in the past. When you factor an expression, then you use something called the zero product rule. Zero product rule. And what it states is that if you have something times something equaling 0, what does that tell you about one of these? One of them has to be 0. In fact, both of them could be 0. So what you do is you set each of those binomials equal to 0. You say, well, either x plus 2 must be equal to 0, or x minus 4 must be equal to 0. That's what the zero product rule tells you. That if you have something being multiplied by something and it equals 0, absolutely one of them had better be equal to 0. And so you check both possibilities. You say, well, either x is -2 or x is equal to 4. And those are our solutions. Those are our x-intercepts. So now again, for an x-intercept, we set the whole thing equal to 0. That means y was 0, and x is either of those. So our x-intercepts then are -2, 0, and 4, 0. Okay. Now that we have both of those pieces of information, we could go ahead and try to sketch a graph of this. So let's go ahead and start our graph. What do we know for sure? We have a y-intercept of -8. So 1, 2, 3, 4, 5, 6, 7, 8. There's our y-intercept. We have x-intercepts of -2 and a 4. So there, with that information alone, do you see the parabola? You can kind of see it there. You got a U shape. There's your parabola. The only thing that we don't have any points that aren't on the x or y axis. And that's why the problem now says create a table of values. And what that means is just find some more coordinates to put on the graph. So what would be interesting? I know that my U shape is going to be something like this. We should have a parabola somewhere that looks like this. The only thing that we're not sure is where's that bottom point? Well, we're not going to talk about solving for the bottom point right now. But it wouldn't hurt if we had a couple more coordinates somewhere in this region so that we could really connect the dots. So why don't we try doing the coordinates for 1, 2, and 3? What the heck? We'll do 1, 2, and 3. So we want to create a table of values. This is often the process you would use. You say, okay, let's make a table of values. My x values, I wonder where the coordinates are when x is 1, 2, and 3. So I'm going to put in 1, 2, and 3. And now I want to find the y value, which is given by the formula x squared minus 2x minus 8. So let's find those 3 coordinates. Now, folks, if you have a graphing calculator on you, this would be a great time to use a graphing calculator. Because you can just go ahead and type in, for instance, notice x squared minus 2x minus 8. I'm going to write that empty. Something squared minus 2 times something minus 8. And so now I can use my graphing calculator and plug 1 into that and just type it out and find the answer, instead of trying to do all that in my head. So I'm going to type in parenthesis 1 squared minus 2 parenthesis 1 minus 8. So parenthesis 1 squared minus 2 parenthesis 1, and then minus 8. I type that all in, and I get -9. I'd like to encourage all of you to go ahead and try this. Like, take out your graphing calculator or your calculator, either way, and try plugging in parenthesis 1 parenthesis squared minus 2 parenthesis 1 parenthesis minus 8, and verify that you get -9. So just take a moment and do that. If you don't have a graphing calculator yet, you could, of course, do this on your phone calculator. It might not be as handy, though. Graphing calculators really are the best because you can use parentheses. And if you have a question right now about your calculator, let me know. I can come by and take a look. Did it work? Did you get -9s? Okay. Well, here's the best part. Once you have -9, depending on your calculator, on my calculator, I hit second enter. If you hit second enter, it brings back up the exact same thing you already typed in. You don't have to type it all in again. And I can just use my arrow and go back and now plug in a 2. So I don't have to type it all in again. If you just hit second enter, which I just did, I can now just overwrite the 1s and put in a 2. So give that a shot. If you have a TI, you should be able to hit second enter. It'll pop back up the formula you already wrote, and then you just use your arrow keys and go back and put in a 2. Okay, so now that time I got -8. And then finally I'll do the 3. So I've got 3 squared minus 2 times 3 minus 8. And again, I can just hit second enter, go back, put a 3 where my 2 was. And now that's -5. All right, so we just made a table of values. Most importantly, what are each of these pairs of numbers? What's 1, -9, 2, -8, 3, -5? What are these? These are all coordinates, right? Input, output. So now what I have are some additional coordinates which are 1, -9, and 2, -8, and 3, -5. And so I'm going to get rid of my little red line that I just kind of sketched in. And now I'll put in those extra coordinates. 1, -9, that's down here. And then 2, -8, that's right here. And 3, -5, that's 1, 2, 3, 4, right here. And look at that. Looks much better. Now can you see the parabola? The parabola is right there staring us in the face. Not only that, but it appears as though we found the bottom of it as well. It looks like the parabola really did bottom out at the coordinate 1, -9. And so now when I make my sketch, I'm a whole lot more confident about what my parabola looks like. Okay, that was a long example. We just looked at a whole host of skills right there, didn't we? We looked at, first of all, finding the y-intercept by plugging in 0. We looked at finding the x-intercept by setting the function equal to 0 and solving, during which we reviewed very briefly about factoring. And then we also made a table of values to find other coordinates that were also on the graph so that we could make ourselves a really nice graph. Now you might say, Mr. G, why do we have to go through all this process of making a graph by hand when I can just go to Desmos and just type in x squared minus 2x minus 8, and we just have our graph. Right? Is this the same graph we just got? Are the x-intercepts -2 and 4? And it was the y-intercept -8, and was the bottom at 1, -9? So we just got all that information by hand. Now, that's going to be one lasting message that I have for you in this class. On the one hand, we could just go to Desmos and just graph any function you like. And you could just do it on your graphing calculator and just look at it. But on the other hand, the skills that we're learning is how to do it all by hand. And that might feel weird to hear, that in class, we're going to learn how to do it all by hand, even though you could just graph it. We have the technology. You could just graph it. But the point of a math class is to learn how to do it by hand and to verify all that information. How does that make you feel? Then what we're going to do in class is learn how to do things by hand that you can actually just do on a graphing calculator. Anybody? What's that, Richie? Yes, 2019. You might say, well, I mean, geez, why don't we just graph it? And you can graph it. Of course you can, and you should, because then you can verify all of the answers that you're doing by hand, right? But in class, like for the test, you'll be tested on your ability to do it by hand rather than, say, just typing it into your graphing calculator and seeing what the answer is. Okay, well, now that you've seen that whole process, let's go ahead and try another one, and this should go a little faster now. Now that we've seen how each of these things work, we can move along and try it on other examples. So, how's about number 2? In number 2, we want to do the same thing. We've got, I'm going to write down f of x equals x cubed minus x. Just to remind myself that y is really f of x and f of x is y. And I'd like to find the x-intercept, the y-intercept, create a table of values, and sketch the graph. So let's start with the easy one, the y-intercept. How do you find the y-intercept? You just plug in 0. I'm going to look at my handy-dandy drawing here. If I ever want the y-intercept, I just plug 0 into the function. So I'll go ahead and do f of 0, which is 0 cubed minus 0, which is just 0. So again, input, output, that makes a coordinate. So my y-intercept is at 0, 0. How about my x-intercept? How do you find an x-intercept?
Set it to 0.
Yeah, you set the function equal to 0. Now really, this drawing right here, like I would tattoo that on your face or something until you have it memorized. If you want the y-intercept, you plug 0 into the function. And if you want the x-intercept, you set the function equal to 0. So now, if you want the x-intercept, we set the function equal to 0. So I'm going to take f of x, which is x cubed minus x, and set it equal to 0. Well, now what do we do with that? X cubed minus x is equal to 0. This is another factoring technique. So we have x cubed minus x. What could I factor out of this expression? You can't factor out an x. So take a look. If you did that, if you factor out an x, then you have what?
X squared.
Yeah, then you just have x squared minus 1. Now you might say, well, what did that do for me? Well, we have to keep factoring. So now how do we factor x squared minus 1? This is a special factoring technique. On this one, we ask the question, what do you multiply to get negative 8 that adds to make negative 2? Joseph? It is x plus 1, x minus 1. So I'm just going to go ahead and write it down. Maybe that jogs your memory, x plus 1, x minus 1. This is called a difference of squares. So I'm just going to show you that formula real quick. Maybe some more examples will jog your memory. If you have x squared minus 25, then that factors into x plus 5, x minus 5. Does that sound familiar? Maybe? Generally speaking, the formula is a squared minus b squared becomes a minus b times a plus b. That's called difference of squares. So that's just a factoring technique from your prior life. So what have we done now? We have now factored this expression down to something times something times something equals 0. So once again, the zero product rule states that if you have something times something times something equaling 0, what must one of those be? Not 1. One of them had better be 0. And in fact, all 3 of them could be 0. So what you do with the zero product rule is you say, well, either that's 0, or that's 0, or that's 0. One of them has to be 0. And so you go through and you solve all 3. This one's already solved. X could be 0. This is x equals negative 1. That's one possibility. And this is x equals 1. That's the other possibility. Those are your 3 x-intercepts. We just solved for the 3 x-intercepts. So what do we know so far? Let's start a graph. What I know so far is that I had a y-intercept at 0. I also have 3 x-intercepts at negative 1, at 0, and at 1. So far that's what we have. Well, right, good question. Bryce just said, hey, is that a horizontal line with 0 slope? Maybe. I mean, just looking at that, can we really tell what the graph does yet? No, because it's a cubic term, first of all, not a squared term. If it was just a squared term, we'd all say, oh, it's a parabola, right? And also, we know that the formula of a horizontal line is y equals b. And this is definitely not y equals b. So it can't be a horizontal line either. So what does it look like? Well, yeah, that's it. At this point, you would need to do a table of values and get more coordinates and start seeing what the graph looks like. Or what could you do? Just type it into Desmos. This is x cubed minus x. Is that what you expected? Maybe, maybe not. But now everybody in the room, go ahead and take your pencil and trace through, and that's what your graph is. Now, how would we have known that without using Desmos? We would have had to sit there and start making a table of values. You'd have to use a table of values, start plugging in lots of numbers, and eventually you'd have a lot more coordinates that you'd be looking at. And then if you connected all those coordinates together, you would finally have a good idea of what the graph looks like. But now just imagine how painfully time-consuming that would be to generate a table of values with like 8 more coordinates so that you could actually see where the graph is. It is very time-consuming. And so the good news is that primarily in this class, I'm looking for your ability to find the x-intercepts and the y-intercepts. And at that point, you can just look at your graphing calculator, see what the overall thing looks like, and then sketch it in. Okay, so is that fair? The primary task we're doing is finding x-intercepts and y-intercepts. At that point, you can use your graphing calculator and sketch in the rest. But there are times when I'll ask you to do a table of values to kind of support your work and show that, yes, that really is what the graph looks like. Okay, well, we're done with that one. I'm going to go right here, number 3. Now, before we do number 3, folks, I'm going to go ahead and write it down as f of x equals the square root of x minus 2. Every once in a while, as we go through problems, you might stop and maybe you're saying to yourself, what's happening right now? What are we doing? Have any of you thought that in the last 30 minutes? What's happening right now? What are we doing? So let's clarify. What are we doing? We're asking the question, what does that look like? Okay, that's what we're asking. We're saying if I just write down any equation in the world, okay, I'm just going to write down any equation like the square root of x minus 2, or over there, 3x minus 2y equals 10. If you write down any equation in the world, you're asking yourself, what does it look like if I graph it? So any thoughts? If I were to graph this thing right now, what would it look like? We don't know. Right? You don't necessarily have the, the ability to just know by looking at it and saying, oh, well, that's what that looks like. We don't know yet. So what we're doing is we're figuring out the process of writing down an equation and then figuring out what the graph looks like. That's what we're doing. Chelsea?
I was gonna say, isn't it an error because of the square root of -2?
Well, that would be if you typed in 0. Correct. 0 cannot be an input. Yeah. Okay, so what does this graph look like? One thing you can always do, just to save yourself the suspense, is you can just graph it. So everybody, what does this graph look like? Square root of x minus 2. That's what it looks like. Okay, that's what the graph looks like. And to be honest, that's what we spend a lot of time in college algebra saying is, if you write down an equation, what does the graph look like? And how do you find out what the graph looks like? And how do you find out what the characteristics of the graph are? So is there a y-intercept? Does it touch the y-axis? No. Is there an x-intercept? Yeah, it touches it right there. And that's all we know for sure, is that you do have an x-intercept, you do not have a y-intercept. Okay, so now that we didn't cheat, but we peeked, right? We peeked and we saw what the graph looks like. Let's go ahead and do this problem according to the tools that we're learning. So first of all, how do you find the y-intercept? The y-intercept is you just plug 0 into f. So you just plug in 0. So f of 0 is the square root of 0 minus 2, which is the square root of -2, which is an error. And so what does that tell you about the y-intercept? There isn't one. Yeah, so there isn't one. We already knew that because we looked at the graph. So there's no y-intercept. None. Okay, what about the x-intercept? How do you find the x-intercept? Yeah, you set the whole function equal to 0. Okay, so we're going to write down f of x equals root x minus 2 equal to 0. And this is what we're solving. The square root of x minus 2 equal to 0. Yes, Karis?
Sorry, I just wanted to ask, for like tests and stuff, if we're writing a y-intercept in there, is there an official way that we write it, or do we just write error?
Oftentimes math books will say DNE for does not exist, or you can just say there isn't one. Okay, so how do we go about solving for x? X is being subtracted by 2 and square rooted. So what do we have to do first? Square it first. So first we square both sides. That cancels the square root. Now we have x minus 2 is equal to 0. And then we just move the 2 over. So x equals 2. That's our x-intercept. Now remember, if that's the x-intercept, x is equal to 2, y is equal to 0. Because remember, we set the function equal to 0. We were saying y equals 0, f of x equals 0. So our x-intercept is 2, 0. And is that what we saw from the graph? Just to remind ourselves, was our x-intercept at 2, 0? Yeah. So again, we are learning to do skills by hand that you can verify by looking at a graph, such as Desmos. Okay, and then how would you find out the rest of the coordinates? You would do a table of values. So all we know so far is that, right? There was no y-intercept, there's one x-intercept, that's all we know so far. How would you know what the rest of the graph looks like? You'd have to make a table of values, and that table of values would give you a bunch of other coordinates, which you could then graph, and then you'd see a bunch of dots, and you'd say, oh, okay, the graph looks like that. But again, the good news is I'm saying once you do the y-intercept and the x-intercept by hand, you can look at your graphing calculator and say, oh, okay, it looks like that. Right? So it's a little of both. We're learning to do things by hand, but we are also absolutely allowed to look at the graph anytime you want. So keep in mind, when you're doing a test, can you just graph it on your graphing calculator? Yeah. You can always just graph it on your graphing calculator and see what the answer is ahead of time. But then you still have to show me how to solve for the x and y-intercept by hand, and that's how you get credit. But the good news is that every problem in this class, you can just graph it on your graphing calculator and know the answer ahead of time. Is that nice? To know the answer ahead of time? I think that's nice. Okay. Everybody, you can cross off number 4. And let's keep going. Okay, so that was all of section 1.2. What did we learn in section 1.2? Let's just review real quick. There were some main ideas in there. 1.2, we learned, we reminded ourselves about y equals mx plus b, about slope, about the equation of a horizontal line, a vertical line, how to find the x and y intercept by hand, and then how to verify it by looking on your graphing calculator. Before we move into section 1.3, how are you feeling? This is a safe space. You can share your feelings. Anybody have any questions or thoughts? Or yes, Brandon.
When you do want us to do the table of values,
yes,
you're going to tell us like how many extra you want to do?
Yes. Yeah, the instructions will specifically say make a table of values and do 3 of them. Yeah, good question, Brandon. How about anybody else? One thing you might be saying is, hey, what was up with all that factoring? Right, we kind of slipped that in there. Well, we are going to review factoring, okay? That comes in chapter 2, that we do a full-blown review of factoring. So if right now that felt a little rusty, like pulling out an x and then factoring it by doing the difference of squares formula and then doing the zero product rule, if you're like, oh yeah, geez, I did that, but it was like a decade ago. We're going to review it, and it'll be in chapter 2. Likewise, for factoring something like this. So yeah, I just kind of threw it at you today as an example, just to kind of spark your brain and remind you that it's something that you've done in the past. But we will do a full-blown review of that when we get to chapter 2. All right, well, here we are, folks, 1.3, Introduction to Functions. We've now used the word function quite a few times, you know, to represent f of x. What is a function? Okay, good, it's an equation. And that's absolutely true. I mean, anytime you write a function, you write f of x equals, and then you write an equation, right? What is a function for? Or what do you do with it? What are some things you can do with a function? Anybody? What? You can graph it. Great. That's one thing you can do with a function, right? Because if you have a function, you can make a table of values. That'll give you a whole bunch of points. You can draw a line through it, and then you made a graph. Or you can just go to Desmos, take your function, type it into Desmos, and you can graph it. So for sure, one thing you can do with function is graph it. And that's definitely something we'll be doing. What else can you do with a function? What? Differential. Well, that's true. Once you get to calculus, you can take the derivative of a function, or you can take an integral of a function. That's true. You can do lots of things with a function. What's kind of the main thing you do with a function?
Solve for x.
Well, that's true. You can set the function equal to 0 and solve. That, in fact, for sure. One thing you can do with a function is set it equal to 0 and solve. And what are you solving for?
X.
X-intercepts. Anytime you set a function equal to 0 and solve, you're finding x-intercepts. But what else can you do with a function? You can just plug numbers into it, right? So that's a lot of different things we just said. What can you do with the function? You can graph it. You can plug numbers into it. You can set it equal to something. What else did we say? Oh, you can differentiate it and integrate it. So a lot of different things. The main thing a function is, and what I want you to write up there at the top of the screen, a function is an input-output machine. So f of x is an input-output machine. All right, that's the whole idea of a function, is that by writing it out in this way, such as f of x equals 2x plus 5, you have an ability to plug in a number and then see what the output is. So if I plug in 0, then the input is 0 and the output is 5. And by saying input output, I just gave myself a coordinate, which is on the graph, which is how you'd even graph a function in the first place, is just generate a whole bunch of input outputs, which are really coordinates, and then you can see what the graph looks like. Likewise, if you find just the right input, such as the input of -5/2, if I plug in the input -5/2, then that gives me 0. And so that gives me the coordinate -5/2, 0. And so that input output happened to give me an x-intercept, right? Because this one would be a y-intercept. If you plug in 0, that gives you the y-intercept. If you plug in something to make it equal 0, that gives you an x-intercept. So while a function is just an input-output machine, you get a lot of good information from that. You can plug in 0 and get a y-intercept. You can plug in a special number and get an x-intercept, provided it equals 0. You could just do lots of input-outputs, generate a table of values, and then graph it, see what it looks like. But fundamentally, a function is an input-output machine. You plug in a number, you get an output, and that's a cool thing. Okay, so what else do we have up here? A function is a relation in which each x-coordinate is matched with only one y-coordinate. So let's talk about what that means. What they have up there is, under the word function, they wrote a definition in a particular way. And I'd like you all to write another definition. So right next to that gray box that says function, I'd like you to go ahead and put, for each input, there is exactly one output. And isn't that what they say? A relation in which each x-coordinate is matched with only one y-coordinate. Yeah, that's said to be a function. So, for instance, in this equation that I just have here, if I plug in 3, what do I get? If you plug 3 into here, what do you get? 2 times 3, 6 plus 5, 11. Is it possible that if I just wait until tomorrow, I could get f of 3 equals 12? Like, is it ever going to equal anything other than 11? No, that's absurd. Of course it cannot. And that's what we're saying, is that for each input, there's exactly one output. And this is basically guaranteed by arithmetic, right? I mean, we're doing arithmetic. If you do arithmetic correctly, according to the rules of PEMDAS, you're only going to get one answer. And that's all we're saying about a function, is that when you do your input, output, everyone in the whole world should agree that when you plug in a particular number, you get a particular answer. That's it. That's what we're saying about a function. Okay. So they also gave us some other definitions up here, which we'll get to. Domain. Do you recall what domain is? I mean, it says it right there. The domain is all the possible x values. The domain is all possible inputs. Maybe write that down. Well, actually, it says it. All possible inputs. You might just want to underline that part. Domain is all possible inputs. And what's the range? All possible outputs. So those are just some definitions. We'll use them. And then finally, when we're talking about a function, and you graph it, one way to know that it really is a function is that it should pass the vertical line test. So let's go ahead and do the vertical line test. We're going to look at a whole bunch of functions here, and we're just going to say, are they well-behaved functions, right? Because you can graph anything. Like, look at this one right here. It's a graph. You know, there's an equation. You type it into Desmos, it'll make it look like that. But this particular one would not be a function according to what mathematicians want to study because it fails the vertical line test. Have you heard that before, the vertical line test? My arm is a vertical line, and it's touching the graph at 2 spots. And therefore, it fails the vertical line test. The vertical line test says that a function is a well-behaved function if any vertical line you draw only touches the graph once. So with a parabola, my vertical arm only touches the graph once, and so we call this a well-behaved function. In this graph, my arm touches that part twice. It touches it not at all, but here again it touches it twice. So this is not a well-behaved function. We'd say this is not a function. Not a function that we want to study anyway. This collection of dots right here, if I draw any vertical line in here, it only touches it once, oops, except for right here. If I draw a vertical line right there, I have 2 coordinates that my vertical line will go through. So this is not a well-behaved function. Why do we even have this definition? Mathematicians only want to study well-behaved functions. Anything else, they're kind of like a separate category, and we don't necessarily study them because they don't have real-world applications. Well-behaved functions have real-world applications, whereas the other ones do not necessarily. Okay, so let's start by just labeling these graphs. Number 7, is that a function? Number 7? No, because a vertical line drawn through -3 will touch 2 dots. What about number 8? Is that a well-behaved function? Yeah, because it passes the vertical line test. The vertical line only touches that graph once. Number 9, is that a well-behaved function? No, because it would touch the graph more than once. How about number 10? Is that a well-behaved function? If you draw a vertical line through number 10 anywhere?
Yes.
Yeah, this is a well-behaved function. A vertical line only touches the graph once. Is this a well-behaved function?
Yes.
Yeah, the vertical line only touches it once. Is this one a well-behaved function? No? Well, I mean, any of these vertical lines are only going to touch that thing once. And even this vertical line right here, that's an open circle, so there's not really a point there. It only touches the graph once. This is a function. It is a well-behaved function because a vertical line will only ever touch one point of the function once. But now tell me, why did you say no? Because there were holes? Or because it was patchy? Yeah, that's okay. There can be holes and it can be patchy. You're just not allowed to have a vertical line pass through it twice. Okay, so that was a function. This one, is it a function? Yeah, it only passes through the graph once. How about this one? Is this a function? Yeah, it only passes through it once. This one, is that a function? Yeah. So again, the vertical line test does it for you. So long as a vertical line, any vertical line drawn only touches the graph once, you're fine, and it's a function. So in fact, all those were functions, weren't they? Right? Yeah, they all were. Okay. So that's the idea of a function. Let me go back here real quick. Let's look at number 1 and number 2, because I skipped right over that. Remember, the main idea is that for each input, there's only one output. And for my example here, again, if I plug in 3, it can only equal one answer. Like I can only have one coordinate that uses the number 3. I couldn't also have the coordinate 312, because that would imply that I plugged in 3 and did arithmetic and got 11. And then the next day I plugged in 3 and did arithmetic and got 12. There's something broken about that. I can't possibly get 2 different answers from arithmetic. So there's only possibly one coordinate that starts with a 3. If I did have 2 coordinates that started with a 3, what would that look like? Here's the coordinate 311. Well, we're just going to go all the way up to 11. And here's the coordinate 312. What do you notice about those 2 points? It wouldn't be a function because it fails the vertical line test. So the vertical line test is just a visual representation of this idea that for any given input, you can only have one output. So just looking then quickly at these coordinates, let's say these coordinates were on our graph. Is this a function? If you knew what the whole graph looked like, would this describe a function? Yeah, because each x value is only used once. -3 is only used once, -2 is only used once, and so on. Over here, though, is this a function? Let's see, -3 is only used once. 1 is only used once. 2 is only used once. 4, oh no. 4 is used twice. 1 minute, you plugged in 4 and you calculated a 2. The next minute, you plugged in 4 and you calculated a -9. That shouldn't happen in arithmetic. And more importantly, what would those 2 coordinates look like? 4, 2, and 4, -9. If you graph them, where would those coordinates be? They'd be vertically stacked on top of each other and it would fail the vertical line test. Okay, so number 1 would represent a function, number 2 would not represent a function. Now, all that said, that's it. It's just this word called a function, where on the one hand, you can write down anything, f of x equals anything, but mathematicians prefer to study things that they consider a well-behaved function that passes the vertical line test. So even though technically I could write any equation here whatsoever, what mathematicians prefer to do is do an f of x equals something that passes the vertical line test, where each input only goes to one output. And that's it. There's nothing else too much deeper to say about it. This is just a definition, and now we're going to move on. Any thoughts or questions about how we use the word function? Okay. So let's take a look here. Here it says, what is the domain and what is the range? Well, wonderful. Domain and range. Who would like to just remind us? What was domain again? All possible inputs. And range is all possible outputs. I'm going to write that down here. Domain is all possible inputs. And range is all possible outputs. Now, the first thing you might ask is, well, what do you mean possible? I mean, I can plug anything in I want, right? I mean, I can just take a number and plug it in. So what do we mean possible? I can type it in my calculator, it's possible. But the question is, will your calculator give you an answer? So remember a moment ago, we had the function f of x equals the square root of x minus 2. What number can't I plug in for x? 0. If I plug in 0, 0 is not a possible input, because if I plug in 0, I get square root of -2, and if I type that in my calculator, I get an error. So is 0 a possible input? No. And that's what we mean when we say possible inputs. We mean, what numbers can I plug in that my calculator will give me an answer? So if I plug in, is 5 a possible input? Yeah, because 5 minus 2 is 3, and the square root of 3 is irrational. It's 1.73 something, something, something. Point is, my calculator gave me an answer, and therefore 5 is a possible input. Okay? So a number is a possible input if your calculator will give you an answer. Rational or irrational, doesn't matter. A number is not in the domain. It's not a possible input if your calculator gives you an error message. So that's one other way to think about it, is all possible inputs, i.e. your calculator will give you an answer. Okay. So what about possible outputs? What does that mean? What's a possible output? I'm going to give you a special function here, x squared. Can I get every possible output in the universe out of this function? Like, could I get the output 25? What would I have to plug in to get 25?
5.
Yeah, if I plugged in 5, I'd get 5 squared, which is 25. So is 25 a possible output? Yeah, 25 is a possible output. Is 16 a possible output? What would I have to plug in?
4.
Yeah, 4. Now, what about 0? Is 0 a possible output? What would I have to plug in? 0. Okay, so far, I mean, I can get a lot of outputs then, right? Could I get the output 6.8? Is there something I can plug in that would give me 6.8? Yeah, something. I just need to find what number squared would equal 6.8, and that would be a possible output. However, is -1 a possible output? What would I have to, can I plug in a number such that that thing squared would equal -1?
No.
Is it a possible output? Why not?
Because a negative squared is always.
Yeah, there's a lot of different ways you could say the answer, but if you square a number, a positive times a positive is a positive, and a negative times a negative is a positive, there's no number that you can square to equal -1. So in this function, -1 is not a possible output. And that's what we mean. Then no matter what you plug into this function, you're never going to equal -1. So that's what we're talking about. Domain is all the possible inputs where your calculator will give you an answer, and the range is all the possible outputs that you could get out of the calculator, right? So that's one thing. That's just the definition. And we've already seen domain, you could have a problem if you're doing a square root, because you can't square root a negative. Okay. Now, how do we figure out the domain by looking at a graph? Okay, this is an important skill. I'm going to give you a new definition for domain. Domain, and you want to write this down, is how far the graph goes left and right. And we actually write it in interval notation using, this is just my handy formula, bracket left to right, bracket. That's the domain. When you're looking at a graph, you're asking yourself, how far will the graph move left to right? So let's try this out. Let's do domain a few times, and then we'll go back and do range a few times. So what's my domain? I'm going to start with number 10. Now, we have 5 minutes. I think we can handily cover the domain examples, and then we'll come back and finish the range examples next time. Okay, so number 10. I want you to look at this graph. First of all, it starts right there, swoops down, and goes up where? To infinity and beyond. And there's a little arrow point there, so it's just going to keep going. So just thinking along the x-axis, how far to the left does the graph go? How far to the left will the graph go? To -2. That's how far to the left the graph goes. How far to the right will the graph go? Infinity. That's already the domain. The domain, I'm just going to put D, is from -2 to infinity. And there's that interval notation. All right, so interval notation tells us that the domain, the graph goes as far to the left as -2, and then the graph stops. But will it continue going to the right forever? Yes. And so the domain is -2 to infinity. And what we're saying is, if you choose any number between -2 and infinity, you're going to be able to find a coordinate on that graph that starts with that number. Like, I can choose the number 5. There will be a coordinate on that graph that starts with a 5. I just have to go over to the 5, and I'll find the coordinate. Choose any number from -2 to infinity, even 100. There will be a coordinate on that graph. If I just go to the far right, eventually I'll get to the coordinate that starts 100 something. Okay? So that's what we're saying the domain is. This is interval notation telling us all the possible x values that you will see on the coordinates of that graph. How about number 11? How far to the left does this graph go?
-2.
Negative infinity. Well, that's an arrow point.
Oh.
Yeah, that's an arrow point. So it goes as it's just going to keep going and going and going and going, and therefore it will keep going to the left forever. How far to the right will the graph go? Yeah, that's an arrow point. It'll keep going and going and going and going. It'll keep going to the right forever. So the domain for number 11 is negative infinity to infinity. And again, what that means is you can choose any number you like, and you can find a coordinate on that graph that starts with that number. So I can just choose the number 13, and sure enough, somewhere on that graph, I'm going to find a coordinate that starts 13, comma something. Okay, that was the domain for number 11. How about number 12? How far to the left does this graph go?
-5.
-5. Okay, now how far to the right does it go?
3.
To 3. But we do have some problems in between, don't we? So for sure, it only goes as far to the left as -5. It goes as far to the right as 3.
Would it be that thing with the union?
Yeah, we have to use a union for this. There is a hole at -3. So can x ever be -3? No, because there's a hole there. There's not really a coordinate there. It's a little open circle. There's no coordinate there. So there's no coordinate at -3. Is there a coordinate at -1? There is actually. So there's no hole there. So I want you to consider what this means. X can be any number between -5 and 3, except it can't actually be the value of -3. So first, let's just make a number line. It's always helpful to make a number line. What numbers are you allowed to plug into that function to get a coordinate? Well, from -5, we have to highlight -3, and we also have to highlight 3. Can I plug in -5? Is there a coordinate at x equals -5? Is there a coordinate at x equals -5?
Yeah.
Yeah, so you can plug in -5. Can you plug in -3? No. Can you plug in 3? No. So what we have here is that you can plug in -5. You cannot plug in -3. You cannot plug in 3. But you can plug in any number in between. Okay, this number line I just made is my number line of inputs. Those are all the possible inputs that will have a coordinate on that graph. And therefore, we want to write down the domain. The domain is simply all possible inputs. So in this case, our domain is from -5 to -3, union from -3 to 3. And that's the domain of that graph. What does that even mean? It means those are all the possible input values. You can choose any number from within those intervals, and that's a possible input that you can plug into the function and calculate a coordinate. And the coordinate would be on the graph. All right, well, I think that's going to be our stopping point because I only have a minute left. So what does this mean for you? We did not quite finish section 1.3. And so that means you do not have to finish all of 1.3 by Monday. That means I'm going to go on to the Moore system and update your due dates. Due on Monday is for sure section 1.1 and 1.2. All of that's due on Monday, so I would immediately start it today. Try to do it while it's fresh. The 1.3, I'll bump the due date for 1.3 all the way to the next week. Because we're not going to finish 1.3 until I see you again on Monday. I'm not even going to see you on Monday because it's Martin Luther King Day. We're going to finish 1.3 on Wednesday. So we're bumping 1.3 all the way to the next week. The next week, that is. Okay, so what's due on Monday? 1.1 and 1.2. Yeah, and I'll change the due dates within the Moore system so it reflects that. Okay, did anyone else still need to give me their student information sheet or their syllabus quiz? Okay, and then will you come see me, Brandon, Karis, and Richie, just so I can touch base with you. Hey folks, when you go home tonight, keep emailing me. A lot of you have already emailed me, that's wonderful, but email me some more. Send me your questions. Yeah. Oh, you know, I didn't bring it with me. But we can head up to my office right now and grab some. Okay, so Richie, how was today? Blast from the past? Okay, yeah, sweet. Oh, okay, great. Oh, well then, fantastic. And thanks for participating. You contributed a few times. That was great. What do I need to say to you? I mean, I'm going to get these things from you. Did you see where you can watch the video online?
Yeah, no, I watched the capture last time.
Okay, okay. So you can finish that. Okay, well, I mean, I think that more or less covers everything. If you have any questions at all, then email me. Okay.
Yeah, no, definitely. I'll just wait at the class.
Okay, great.
You have office hours?
I do. Everyone, I do have office hours right now.